Greetings everyone. Today we're going to start talking about fluids, specifically buoyancy. Why do some objects sink or float, and how can we describe this mathematically? Let's start first talking about density. We're all familiar with density. This is just the mass over the volume. In SI units, we can use kilograms per meter cubed, but you'll also commonly see grams per cubic centimeter. And here's some numbers for water. So water is 1,000 kilograms per cubic meter, or more easily, we could use the units grams per centimeter cubed. You may also see 1 gram per milliliter. So 1 milliliter is the same as 1 centimeter cubed. So then we can compare why some objects float or sink just based on this density. We know if things are not very dense, like I don't know, a basketball or something like this, and we try to place it into water, right? It's going to sit, and just part of it is going to be submerged. So it's floating on the surface. Whereas if you put a rock in the water, the rock is going to sink all the way down to the bottom. And this is because rho of the rock is greater than rho of the water. So we could also talk about things in terms of specific gravity. So this basically just divides, well, the rock over rho of the water. And this gives us a nice little ratio called the specific gravity. And in this case, this is going to be greater than 1. So for things like a fish, which just sit basically floating in the middle of the water, not floating at the surface or sinking all the way to the bottom, it's just kind of hovering there. These are called neutrally buoyant, so its specific gravity is just equal to 1. So another important concept with fluids is the concept of pressure. And pressure is force per unit area. So in our SI units, these are pascals, or 1 Newton per square meter. So just to give you a concept of how big is a pascal. So atmospheric pressure is, well, it's about 15 psi. So this is pounds per square inch. And then this is also equal to 1.01 times 10 to the 5th pascals, or Newton meters squared. So you need quite a few pascals to make it to atmospheric pressure. So this is a very small unit. So in a fluid, the air could count as a fluid, water is a fluid. We can take, all right, here's our surface, and we're going to have some object sitting in the water. There are forces in all directions on this object. The water is pushing in above, pushing in on the side, pushing in from the bottom, pushing in from this side. And so the area that we're talking about is all over this object, basically. So this is why things that go deep down, like Jacques Cousteau's submarine or this deep sea anglerfish, these are always really small. Basically, if you have a small amount of area, then you need a small amount of force to compensate for that pressure, or you'll be crushed. So as you go deep down into the water, the pressure increases. And this pressure increases linearly with the depth of the water. And this is because as you go down further, there is more water on top of you. So the only thing that matters is this H, and of course the density and gravity. But it doesn't matter how big the container is. Like, you don't get more squished jumping into the ocean than jumping into a pool because there's more water to the side of you. The only thing that matters is how deep down that you go. Another way to think about this is this pressure that you go down is going to be equal to whatever pressure up here plus that rho GH. This rho GH is going to be equal to this, but then if you want to compare this to the total pressure that you feel, then you need to add on this atmospheric pressure. So there's also all of this air up above you, above the ocean, that's pushing down on the ocean. So to get your total pressure on you, you have to add this onto that. So let's work our problem. So what is the pressure at the bottom of a swimming pool that is 22 by 12 in its cross-sectional area? So if here's our pool, this could be 22 meters, this is 12 meters, and we're going to say that it's just a nice box pool, and this is 2 meters. All right. So what is the total force exerted on the bottom of the pool, and also what is that pressure? So the pressure is equal to this rho GH. So all we need to think about is what is this H? So this is 1,000 kilograms per cubic meter. That's the density of water, times G, which is 9.8 meters per second squared, times H, which is 2 meters. So this pressure, just due to the water, is equal to 1.2 times 10 to the 5th newtons per meter squared. So we could also convert this into atmospheres, and this is about 1 atmosphere. It's a little bigger. So then the total pressure on us, we add on the atmospheric pressure, is going to be 1 atm plus 1 atm is about 2 atmospheric pressures. So going just 2 meters down in your pool, you end up putting twice the pressure on your body. So this is why it's really hard on your lungs the farther down that you dive. So what is the total force exerted on the bottom of the pool? So we can use pressure is equal to force over area. And so what we want to do is to find this force. So force is then equal to pressure times area. And this total pressure is 1.2 times 10 to the 5th Pascal. And then times our 22 meters by 12 meters. And this is going to give us a total force of 3.2 times 10 to the 7th newtons. So we can also use this relationship of pressure in a fluid, so F over A, in order to help us do work. So if we have, if we want to pick up something very heavy, like maybe a car, that's a car. Then you've heard of hydraulic lifts, and this is the principle that is at play here. So the pressure is equal to the force over the area, and this pressure only depends on the depth of the fluid. So if we look at the fluid at a certain depth, let's say right here at the top, then this pressure, let's change color, then the pressure right here is going to be the same as the pressure over here. And the pressure right here will be the same as the pressure over here, because it's only going to depend on the depth of the water above it. And so what is the pressure of the water here? So the pressure here has to be the same as the pressure over here. And this is so that everything is nice and force balanced. So here, if we didn't have the same amount of pressure, we had less pressure here, then the water would rush in to this point, basically. And this, we know this doesn't happen. So the pressure down here is the same as over here. So if the pressure here is equal to the pressure here, then we know that, let's do this, then we know that F1 over A1 is equal to F2 over A2. So just comparing the two forces that we exert here and here. So then if we have F1 over A1 is equal to F2 over A2, then we can solve for F1, and then we'll get A1 over A2. So here's a way that we can multiply the force that we apply. So if we apply a small force here, then it's going to be the ratio of the two areas. It's going to be the force that we can basically exert here in order to lift this car. So let's work out a problem and see how this principle works. So here we have the same scenario that we had before, but here we have a few numbers. So this diameter is 2 centimeters, and then this connects over to a place that has 10 centimeters. And then here we have the car, M car G. And we want to know what force do we apply on this part in order to help pick up the car. So here we have F applied over the area that we apply is going to be equal to basically the force of the car over the area of the car. And then we solve this for the force applied. So this is equal to the force from the car that we're trying to lift, AA over AC. So let's plug in a few numbers now. So F of the car is going to be the mass of the car times 9.8 meters per second squared. And then now the ratio of these two areas, so pi, and our applied area is going to be 1 centimeter, so 0.01 squared, and then divided by the area on this side. And so the force that we need to lift this car is 390 newtons of force. So this brings us to buoyancy, Archimedes' principle. And this kind of wraps up all the topics that we've been talking about today. So the buoyant force is equal to the density of the fluid times this is the displaced volume of the fluid, times the gravity. So you can check out the units here, you're going to get newtons. So where does this come from? This feels pretty strange. Why is it the volume of the water? This is of the water, not of the object. So where this comes into play is that there is an imbalance of forces between the top of an object and the bottom of an object, because objects aren't infinitesimally thin. So an object has some thickness, right? Then there is some height that is at the top of the object and some height at the bottom of the object. So there's a pressure at the top that's different than the pressure at the bottom. So there's a force at the top that's different than the force at the bottom. And you can work out what this buoyant force is. But here we have a lot of stuff that we may not know anything about, which is this area up here, area down here, times its height. And we may also have like funny shaped objects like this that may be floating in the water just in the middle. So how can I talk about this? So this is really actually pretty complex, but where it becomes simple is that this buoyant force is equal to rho of the fluid times the volume of the displaced fluid times G. So back 200-ish BC, there was a hero who gave some gold to his smith to make a crown for a temple. But he suspected that this goldsmith cheated him. So he asked Archimedes to find out if this goldsmith cheated him or not. and if he mixed any baser elements into the crown. So how can we find out if Hero was cheated or not? So the first thing you could do is you can go, well, we know the buoyant force, right? This is equal to rho of the fluid, G, and then V, the fluid displaced, right? And we know that if we put the object in, we're going to get some buoyant force. So the first couple of things that we need to do is write down some of the things that we know. Let's just say that the mass of the gold that Hero gave was 1 kilogram. And then this needs to fit on somebody's head, so the diameter of the crown is so big. So this means that our container has some cross-sectional area. Basically, we're going to take this crown and stick it in a bucket, right? This could be one way we could figure out the density, right? So if we put it in a bucket, the bucket now needs to have a diameter bigger than the crown so we can fit that in. And then we can put the crown in and measure how much water is displaced, right? So we can measure V displaced. Just like if you fill up a cup too much with water and then now you put ice in it, now stuff spills over the edge. So this is what we're going to do, right? So if it's 100% gold, we can look at the density of gold that we know, and then we know the volume that should be displaced. So that's working out here. We know that this buoyant force should be equal to mg, right? And if it's equal to mg, then it's equal to rho of the object times the volume of the object times g. And then this should be equal to rho of the fluid times g times v that's displaced. So that means that this volume that's displaced, if it were 100% gold, would be 52 centimeters cubed. And this would mean that the water would rise this far, basically. If we're not spilling it out and trying to catch it, we just measure, how much the water rises, this right here. So let's say that this goldsmith did cheat Hero. So it's going to be a 70-30 mixture between the gold and the silver. So the density of the silver is this, and we can work out what the volume of the water displaced would be. So we have this much water that's displaced, and then we'd get a height that raises up this big. But we have a problem here because this is 200 BC and it would be very hard to measure this height differential. Well, what Archimedes actually did was he took a measurement of this object, so of the crown. There is a tension up and there's mg down, and so then the sum of our forces is going to be T minus mg equals 0. So this means that T equals mg. And if the goldsmith didn't cheat him, there should be 1.00 kilograms times 9.8 meters per second squared. So this is 9.8 newtons. So if the goldsmith did cheat him, he took some of the gold away, but then he can replace it with silver to match the weight. And this is what the goldsmith did. So he can make this work out by adding on silver. But where things get complicated is that now Archimedes said, well, you can't cheat nature. I can take this thing, submerge it into water, right? And now what are my free body diagram look like? So I have T, I have mg, and now I have a buoyant force. So the goldsmith didn't account for this buoyant force, right? So now the sum of my forces is going to be T minus the buoyant force, plus the buoyant force minus mg equals 0. So then this T is equal to mg minus the buoyant force. But what is that buoyant force? That buoyant force is equal to rho of the fluid times g times the volume that's displaced. So since both the pure and the impure are going to have this mg, let's just think about this buoyant force. So this buoyant force is going to be rho of the fluid, so that's 1 gram per cubic centimeter. And then both have g, so let's just think about this piece, rho, and then v. And then now the volume that's displaced is 51.8 centimeters cubed, and then now we can have our g right here. So this actually gives us the same as like 51.8 grams. And then if you wanted the force, you'd have to multiply this by g, which is the acceleration due to gravity. But here, what we're going to get is that this buoyant force would be the same as 51.8 grams of the fluid being displaced. So the 70/30 is going to be the volume that's displaced is the 64.8 centimeters cubed. And then now we times this by the 1 gram per cubic centimeter. And what we get is 64.8 grams. So what this means is that you don't need to measure the fluid that's displaced. What you can do is you can measure the weight differential. So this is 13 grams of the fluid is going to be different than if this were pure. So what you can do is you can set up a scale, right? And then you can hang the two objects here. Well, we can put our 1.00 kg of gold, pure gold over here, and then now we can do our crown over here. So this crown should have been 1.00 kilograms of pure gold, but let's say that it's 70/30. So what this means is that if you weighed this in the water, there's going to be more buoyant force on this impure part, right? The buoyant force is bigger than this one is. So it's going to tip the scale like this. And so you're going to know that this was made out of baser elements in addition to the gold, but it's not as dense as this gold is. All right, let's consider one last problem that is not quite as tricky as the last one, but it's still very informative. So what is the density of this duck? So let's look at our duck. The duck is floating in water, and we're going to say that 29% of its volume is below the water. And that would leave us with a nice 71% above the water. That's the part of the duck that we can see. So what is the density of the duck? So what we're looking for is rho duck. And rho duck is going to be the mass of the duck over the volume of the duck. But the thing is, I don't know either of these. So this is not going to be the way that I need to solve this. So let's look at the buoyancy force and look at our free body diagram. So what are our forces that we have here? We have mg and we have a buoyant force. So we know that the sum of our forces is going to be the buoyant force minus mg, and that should be equal to 0. So that means that our buoyant force is equal to mg. All right, I still don't know the mass of the duck, so what can I do? But I do know that the mass of the duck is equal to rho of the duck times the volume of the duck. So let's write out mg over here. And so this would be mg is equal to rho duck times volume of the duck. And then now let's write out what this buoyant force is. So rho of the fluid times the volume of the fluid that's displaced, now times G. And this will be times G2. So we have G's on both sides. We can kind of get rid of that. So this volume that's displaced is actually 0.29 times volume of the duct. And actually we have ducts on both sides too, the volume of the duct. So what we have is rho of the duct is equal to 0.29 times rho of the fluid. But the rho of the fluid is water, which we know. So that's 0.29, and then now we can do this in kilograms per cubic meter, or one that's a little nicer to write, grams per cubic centimeter. So the rho of our duct is equal to 0.29 grams per cubic centimeter.